Swayam Prabha. Digital India. Educated India.
Once again I welcome you this lecture, and I have mentioned in my last lecture that I have completed the shear strength aspect, but still I want to take one more lecture on it, highlighting the important aspect, because it is a very important. Shear strength is very important in soil mechanics and geotechnical engineering. So, I want to summarize whatever we have discussed in shear strength, highlighting the important points. So, let me do one by one or all important points. Suppose I have initially I have discussed about source of shearing strength. We have mentioned, you can see that frictional resistance to sliding between the solid particles, then cohesion and adhesion, and interlocking and bridging of solid particles. So, sometime this, why I am highlighting this one, sometime in a competitive exam. So, where the MCQ will be there will be certain statements will be given and it will be asked, find out the statement which is not correct, or how many statements are correct, how many statements are wrong. So, if you understand or if you keep in mind this point, important point, then you will be able to do that. Next one, you can see that as I have mentioned before, the initial stage, that at any point actually you can in soil mass you can find out, and there actually state of stress you can define in 3-dimensional form. And finally, I have mentioned that for most of the application we can we can use the 2D biaxial form, and most of the application it does well. And if we in biaxial format, if you know the state of stress, then we can also find out the stress at any orientation, the plane with any orientation, that is what. And if the plane is oriented with theta as is given here, then on that plane sigma and tau and is given here, and where actually sigma 1 sigma 2 become maximum, that is actually theta also I have given that expression. So, these are the things to be also remembered. Sometime many frequently you may use here in when you will do the problem in shear strength. Next is you can I have also shown that the whatever value at a particular plane orientation theta can be anything. So, with the variation of theta, whatever value we are getting tau and sigma, and we have shown that those locus of that point is a circle, and that equation of the circle we have shown before, that it is like this, with center at sigma x plus sigma y by 2 0 and radius equal to this. This is also I have highlighted. And another important thing I have mentioned, that use of Mohr circle. If you know the state of stress, from there you can draw the Mohr circle, and this is the various aspect of the Mohr circle. You can see if the origin is chosen here, and if you know the sigma 1 value or sigma 3, then I can get these two terminal points, and this will be the diameter. So, half the point take as a center, draw the Mohr circle, and there we can find out many things. Or if the state of stress of a particular point is given, from there that point will be if this is a element, and this side is given, it will be unique point will come here, and similarly this and this, if it will come here. So, that means if you can get this point and this point, automatically I again get the diameter, or if I know the sigma x sigma y, I can find out the radius, then I locate the radius center and locate one point and draw the circle, get the Mohr circle. After the drawing the Mohr circle, I will read this is maximum shear stress, this is maximum normal stress, this is minimum normal stress, and if I want to find out what is the normal stress and shear stress at any plane which is oriented theta, suppose this is the plane. So, I will rotate theta like this, then it will intersect it here. I will directly read the value here from the circle, we will get the normal and shear. Similarly, principal plane and principal stress I have mentioned. You can see the principal plane, a plane that is acted upon by normal stress only. That means, if one element is here and this is there, and another element is here, and shear also is acting like that. So, this plane is not a principal plane, whereas this plane is principal, because there only normal stress is acting. And similarly, principal stress, the normal stress acting on principal plane is referred to as the principal stress. That means, on this plane where there is no shear stress, that plane whatever normal stress acting, that is a normal principal stress. At every point in a soil mass, applied stress system that exists can be resolved into three principal stresses that are mutually orthogonal. The principal planes corresponding to these principal stresses are called major, intermediate and minor principal planes, are so named from the consideration of the principal stresses that act upon them. The principal stresses sigma is known as the major principal stress act on the major principal plane. So, this suppose sigma 1, major principal, this is sigma 1, this is our sigma 3. So, this is already I have elaborated before. So, once again, what is principal plane, what is principal stress, once again I am summarizing here. And this is the thing, suppose this is the major principal stress direction. So, major principal plane will be this one. Similarly, if this is the minor principal plane, so this is the minor principal stress. And if this is the one, then theoretically we can express what is the value of tau and sigma n in terms of sigma 1 in terms of sigma 1, sigma 3 and theta. If the plane I orient, if I know sigma 1 and sigma 3, and if I know the value of failure plane, then on that plane what is the tau, what is the sigma n, I can find out by using this expression. We have also a little different form of equation also, that they are same. If it is trigonometrically, if you simplify, it will get another form. So, that is also I have shown before. And you can see the relationship between theta, that means failure plane, and the phi, that is also important. So, if I know the phi value, I can automatically find out the value of theta, that inclination of the plane with the major or minor plane. So, 45 degrees plus pi by 2, how it is done? This is the envelope and this is the Mohr circle. Then if I join from here to here, this is a right angle, and this is, if this is 2 theta, if this is right angle, and this will be a symmetric triangle, because these are same and this is also same. So, this will be theta, and from there actually if I consider a triangle, this triangle, from that triangle, the ODC triangle, 3 angle summation will be 180 degrees. From there we get theta equal to 45 degrees plus pi by. So, this is also another important thing to be remember. And we have mentioned that shear strength in terms of total strength, total stress parameter, this is the equation. In terms of effective stress parameter, this is the shear strength equation. This is a Mohr Coulomb equation, and this is a general form of equation, but when sand, then C will be 0. When sand, it is C will be 0, that means for sand the equation tau will be equal to sigma tan phi, whereas when it is a clay, phi equal to 0, for clay tau will be equal to, it is nothing but Cu. And this is one form of equation, shear strength equation with phi and shear parameter. and then this is another expression also we have given, that is actually sigma 1, sigma 3 and phi of the soil, phi c. Sigma 1 major principal stress, minor principal stress, and C and phi, they have also relationship. This relationship also important now, and very frequently we use if you do not have graph paper, and if you want to do analytically, then this is the equation sometime useful for getting the value of C and phi. When you use total stress parameter, this is the equation. When you use effective stress parameter, this is the equation. So, they are same, only wherever there is a total stress is there, it has to be replaced by effective stress. So, sigma 1 will be replaced by sigma 1 dash, sigma 3 will be replaced by sigma 3 dash. And for determination of shear strength parameters, we have mentioned, once again I am summarizing, there are 4 different methods, there are many other methods also, but it commonly in undergraduate level we cover these are the 4 things: direct shear test, the triaxial test, unconfined compression test and bend shear test. And again triaxial test will have several things that I will summarize in the next one, and unconfined compression test and triaxial test, only difference is that unconfined compression test there is a no self pressure is applied, that is sample is unconfined. And your during the triaxial test, we apply the confining stress, and then we apply deviator stress, and schematically or stage wise how we do, or finally what we get, sometime we have to understand. For that I have also brought this one here. You can see during the test, this is the condition: you have sample subjected to sigma 1 this side at failure, and sample subjected to sigma 3 this direction. This is the final form, but this final form is developed based on this. Initially we apply sigma 3 all around, and then later on we apply sigma, that is deviator stress, sigma 1 minus sigma 3. So, this is called deviator stress, and sometimes this is called principal stress difference, and that is called principal stress stress difference. Sometimes it is called additional axial stress. So, any term is used, so you have to understand they are same, and they are sometimes that will be used as delta sigma, sometimes it will be delta sigma d, like that, and at failure of course sometimes it will be additionally f will be given. So, if this is the one schematically or symbolically given, you have to understand that the second stage of shearing test, during shearing whatever we apply, this is these are all same. And as I have mentioned that triaxial test is a universal test. You can simulate the actual field condition or close to the field condition, and to do that we have several mechanism of test. One is unconsolidated undrained test, consolidated undrained test and consolidated drain test. There are 3 different tests are there, and unconsolidated undrained test actually we apply confining pressure, and immediately by applying deviator stress we go to up to the failure, and it takes very little time, and we get from there only undrained shear strength Cu. Whereas, consolidated undrained test, initially by applying confining pressure we consolidate that sample, and later on we shear by applying the additional axial load, but without draining. And whereas, consolidated drain test we consolidate in a similar way as it is done in the second one, but in the second stage while shearing we also allow drainage, so that in the during the test never there will be any pore pressure. So, this test actually it is a very it takes long time, maybe sometime week long. This test actually 1 day for consolidation, and for shearing maybe another half an hour. So, altogether this may take 15 minutes to half an hour. So, for routine work we do this, but for some important work we need to do either this or this, but these we do occasionally. We do this one with additionally measurement of pore pressure during the shearing, and that from there actually we can get the result of this drain test. That detail I have shown. Once again I will show you how to do that. So, as this is also I have summarized that when you do undrained shear during UU test, during UU test on saturated sample we get a undrained shear strength independent of confining pressure. That means, if you measure the pore pressure also during shear, and if you finally convert into a effective stress circle, you will get only one circle, and the circle size also will be same, and that is what it is shown here. The shear strength envelope will be tangential to this. So, that means, this one will be the half the diameter, and the diameter is nothing but sigma 1 minus sigma 3. So, that can be so that one can be obtained by this we have given before. And for CU test, if you do CU test, consolidated drain test, you can draw the circle here, this, and common tangent if you get, you will get a phi u, as I have it is mentioned, and I have also mentioned that CU test can be utilized as a CD test by the measurement of pore pressure during the shearing, and if you measure the pore pressure additionally, and finally whatever confining pressure you applied and whatever confining pressure additional principal stress you have got at failure, they are subtracted. If the pore pressure is subtracted from that, you get the effective stress, and those effective stress corresponding effective stress circle if you draw, and from that circle if you draw a tangent, you will get another envelope which will be steeper than the earlier one, and from there whatever angle we will get, that is actually effective stress friction angle. So, that means, CU test both total stress friction angle and effective stress friction angle we can get. So, this also we have discussed before. Once again I am highlighting here, this is since it is important. And for unconfined compression test, as I have mentioned before, that your sigma 3 is 0, and this is the QU, and QU nothing but sigma 1, and then if I want to find out, your envelope will be horizontal, and then that means at a distance of r. So, r is CU equal to sigma 1 by 2 equal to QOE bar. So, unconfined compression test, sometime if it is unconfined compressive strength is given, then from there you have to find out CU, undrained shear strength is just half of that. And different stress and behavior of different soil, this is also we have explained, and this one has to know. If sensitive clay without disturbance, then this is the one, and if it is a remolded same soil, if it is remolded, then we get a stress and behavior like that, and if it is insensitive clay, normally that is not sensitive, then we get a curve like this. And during the shearing, the soil can fail in different ways. That is one way of failure, that is shear, prominent shear plane it is show, and some soil without showing any prominent failure angle, it will continuously decrease in length and increase in diameter, but to terminate the test, generally we stop the test at around 15 to 20% strain level, and some soil may fail both shearing and barreling together. So, it will shear, prominent shear plane also will be seen, also there will be some volume bulging also will be observed. And this is also behavior of normally consolidated, over consolidated, this is over consolidated, normally consolidated, this is the volume change of over consolidated, normally consolidated, this is we have explained elaborately before. So, once again I am repeating or summarizing this one here. And this is actually again stress strain behavior of the sand. Again if it is loose or if it is a dense, dense is this, loose is this, and this is the value both will reach at large strain value. Ultimate stress for both loose and sand will be nearly equal, and for dense soil actually generally volume increase will be there at a after certain strain rate, whereas loose sand will be continually decrease in volume, and correspondingly we can find out what is the critical void ratio. So, critical void ratio, as we have the we can see if the from this diagram what we can conclude, if the soil is having void ratio with greater than critical void ratio, that means that is the soil is loose, and during shear it will have decrease in volume. Decrease in volume means sorry so void ratio is large, that means loose, that void is large, and then it will be the continued volume is decreased, means volume void ratio will be decreasing. Whereas, if the void ratio is lower than the critical void ratio, that means void ratio is less, means it is dense, and when shearing its void ratio will be the volume change will take place, but volume will increase, and then that because of that your void ratio volume will decrease, and because of that your void ratio will be increasing. So, finally, that it will reach to a constant value, whether it is loose more than more than critical or less than critical, and if you increase the strain level, both will come to a common value, that is equal to critical void ratio. And finally, as I have mentioned that either normally consolidated or over consolidated or loose sand or dense sand, we can do different test. For example, direct shear test is suitable for sand, for saturated sand and all can be done by either direct shear, either triaxial or different triaxial test we can apply for both corrosion-less and cohesive soil, and unconfined compression test can be done for only saturated cohesive soil. And we have also mentioned that in some soft sensitive soil sampling is difficult, or maybe sampling can be done, but during this process, that sampling process, its effect, its properties changes change significantly, and those soil, instead of doing sampling directly, in situ test can be done, and one such in situ test is a vane shear test. And vane shear test that details I have shown before, and there will be 4 blades welded to the rod, and they each between the 2 vanes there will be angle will be 90 degrees, and that vane will be pushed inside the soil vertically and rotated by applying a torque, when the resisting torque of the soil will be same as the or applied torque is greater than the resisting torque of the soil, this will show the indicate the failure. And so, that from that condition we can actually find out the value of Cu. So, the applied torque is this, and in terms of Cu and the blade dimension we can express this, from here I can find out Cu. Okay. And similarly, when you do vane shear test, the resistance may be there from both top and bottom, sometimes it may be only from bottom. So, if you consider only from top only both from top and bottom, then this expression can be used, and if there is no resistance from the top, only resistance at the bottom, then this equation can be used. So, this is the main shear test. Directly we can get the value of earned shear strength of the soil. So, by and large this that is all about shear strength. I think I will go to the next topic maybe from the next lecture. With this I conclude shear strength topics. Thank you.